Okay, we're back to finishing off our first lesson in the series after the AP exam. This time I want to talk about something called differentials, and you've seen this before. You've seen this notation dy dx, right? That represents the derivative of y with respect to x, and it's treated like a single entity. However, you can also look at these quantities, dy and then dx, as separate things, in such a way that the ratio of dy to dx is equal to the derivative. When you look at it as two separate things, we actually call them differentials. And it's useful in finding approximate values of functions. So when I say let y equals f of x, where f of x is a differentiable function, then the differential dx is like the independent variable, and it can be given a number or a value. Then also the differential, which is dy, is then defined in terms of dx by this equation, dy equals to f prime of x dx. Now you're like, where'd that come from? Where'd that come from? Well, don't freak out. Remember, dy dx is the same thing as the derivative. Now we're going to treat these as two separate entities. So I can take the dx part and move it to the right-hand side. And then you have dy equals to f prime of x dx. Ta-da! So once again, we can use this to actually help us approximate values. So I want you to compare the values of delta y, which we know is the change in the y value, with dy, if in this case y is this particular function, x squared minus 4x plus 3, and x changes from 3 to 3.05. Now, how do we find delta y? Well, delta y is the same thing as the change in the y values. So really taking the y value at 3.05 and subtracting it from the y value at 3. And if I did that by plugging it into the equation, this will be 3.05 squared minus 4 times 3.05 plus 3, right? Once again, just plugging it into the equation. Minus, and then if I had f of 3, that's 3 squared minus 4 times 3 plus 3. You can do all these calculations, and oops, whoa. And if you did it properly, you would have found the answer, I think, was 0.1025. Okay? So you're like, okay, that's the exact value of delta y. That was a lot of work, though, right? Lots of work, lots of work. So instead of doing that, we can use this equation, dy equals to f prime of x dx, to help us do an approximation of the actual value of the change in y. So if you do this, what's the derivative here in this case? Well, the derivative of x squared minus 4x plus 3, that's just 2x minus 4. And then we have to multiply that by dx. Well, what are these particular values? The x value here is the number 3, so I'll just plug in 3. What is dx here? Well, dx is just the difference between the actual and the value. So in this case, that'd be 0.05. So I can replace dx with 0.05. 6 minus 4 is 2. 2 times 0.05 is equivalent to 0.10. That's pretty close. Okay? So I know the equation was nice and simple, but when you do more complicated things, then, hey, this derivative method might be a lot faster. Okay? So let's take a look at the next one. Here I've tried to apply it to a situation. You got a radius of a circular disc. It's given as 24 centimeters, but we know there is error in your measurements, and the error, the maximum error that we have, is 0.2 centimeters. Okay, so that's the error in, that's the error in the measurement for the radius. I'm asking you to use differentials to estimate the maximum error calculated in the area of the disc. So for those of you doing engineering projects, you might need to figure out error tolerances of like materials or whatnot. So you can use these differentials to help you calculate it. So if there's an error in one variable, how large is that error in another variable? Of course, those two variables have to be related. So in this case, what is the connection between these two variables? Well, area equals to pi r squared for sure. And so if that was the case, you're looking at our equation now, not dy equals to f prime of x dx, it's dA equals to f prime of r, because r is our independent variable, times dr. Well, if area equals to pi r squared, we know that the derivative will be, that's right, 2 pi r. So your dA, your differential, your change in A, must be 2 times pi times the radius at that point. What is the radius at that point? I told you it's 24. And dr, so that's like the error, right? Dr is like your error in your radius measurement, and that will be 0.2. So if you did this calculation now, 2 times 24, that's 48. 48 pi, 0.2 is a fraction 1/5, so how about 48 pi over 5? And if I were to do this calculation in my head, that's approximately 30 centimeters squared. So a 0.2 centimeter difference at the point where the radius is 24 could give me an error of approximately 30 centimeters squared in my calculation for its area. And then sometimes you'll see questions like this where it says, what is the relative error? Okay, relative error really is just the change in the y value divided by the actual y value. It's like a percentage, right? How bad is it? We can, of course, now use delta y and replace it with dy. So therefore, we have now an easier way of calculating this. And so for the relative error of area, I would say that's dA over A. Well, we calculated dA from the top. That's 45 or 48 pi over 5. The area calculation is just pi r squared. That's 24 squared. And now I'm thinking if I do that, 48 over 5 pi. This is pi times 24 times 24. Notice the pi's cancel out. The 24 and 48 reduced to 2 and 1. So now I'm thinking this is the same thing as 2/5 times 1 over 24. That simplifies to 1/12, and yes, I got 1/60th. So really the relative error here is just 1/60th of the original. So not that large. Okay? So that's differentials. I want to do the last thing here is something called Newton's method. These are, once again, just topics that I didn't cover in the AP course, yet I know sometimes these are done in first-year university courses for the differential calculus section of the course. So if you're at UBC, that's Math 100. I think SFU Math 151. Forgot what the course is at U of T, but I know they do this stuff too. So that's why I thought I would go through this with you first. All right. Newton's method. So Newton, remember him? Yes, the guy at the apple. He came up with a lot of things. Not only did he come up with calculus and all this stuff in physics, he also found this, Newton's method. Let me show you what this is. So this is a method used to find roots of an equation of this form. So that equation equals to 0. When you do this, though, you have to start off with an approximation, which we call x sub 0 or x naught. So we have to choose some value. And you do that by guessing. Now, in order to see if that guess was good enough to approximate the 0, we have to then consider the tangent line to the curve at that particular point. So, do you see this diagram down here? Do you see this red line or red curve? That's the graph of f of x. Let's assume that I chose x naught, that's over here, as my initial guess for the 0. It's pretty far off from the 0, right? The 0 is this red dot, so not so great guess. But that's okay. This is what Newton said. If you were able to find the tangent line at that point x0, and that would be the blue line, then we can just find the x-intercept of that blue line. Because that x-intercept of that blue line will be a better approximation than your x sub 0. And it is, right? It's closer. Well, if you want to actually get even closer, you just repeat the process. You now go ahead and take that x sub 1 and do the same thing. Find the tangent line at that particular point, and then find the corresponding x-intercept of that tangent line. And you keep doing this, and I hope you can see that as you keep doing this, you get closer and closer to that red dot, which is your x-intercept, really quickly. And therefore, depending on how accurate you want your answer, you just have to limit the number of times you do this. You'll then get the actual x-intercept. Now, by the way, this is what your calculator does, your TI-83 calculator, when you ask it to find the zeros. Okay, this is pretty much what it does. It takes a guess, because that's why I always ask you for a guess. within a range, and then it just repeats this process until it gets like 9 decimal place accuracy. Okay? Now, how do we formalize this? So remember, the idea was we took a point and we put it into the tangent line. So what is the equation really of a tangent line here? Hopefully you remember, equation of a tangent line. I'm going to use point slope form. Yeah, it's y minus y1 equals m bracket x minus x sub 1. In this case, if I were to use the tangent as x equal to 0, we now have y minus y1, which is the actual y value when x is 0. So I'm going to use this notation, f of x sub 0. We would be looking for the slope at that particular value. That's f prime, right? That's the slope. Remember, slope, derivative, same thing. And then now our x sub 1 value would be our actual x sub 0. So this is the equation of the tangent line, the one in blue. Maybe I should have actually did this in blue, but oh well. Your goal after finding the equation is to find the x-intercept. So now our goal is to find the x-intercept. How do we find the x-intercept? We let y equal to 0. So we'll make y equals 0, and now we have this expression. And if I ask you to now solve for x, I'm going to now probably try to isolate this x. So I'm going to move the derivative over to the left side. So negative f of x sub 0 divided by f prime of x sub 0 equals to x minus x sub 0. And then isolating x, I will put the x sub 0 on the left side. X sub 0 minus f of x sub 0 all over f prime of x sub 0. This then becomes my new x. This is my new x. Sorry, I shouldn't say new. This is my x-intercept, which actually becomes what? X. This is my x-intercept that becomes my new guess. And then we repeat the process again. So really then, if I wanted to generalize this, in general, if the nth approximation is x sub n, provided of course that the derivative is never equals 0, then the next approximation given is what? Well, I'm just going to reverse this around. I'm going to put the x as x sub n, so I'm going to take this here, okay, and pretend that that's x sub n. So I'm going to generalize this. So the x sub n value is always going to be equal to what? It's going to be equal to the previous value, right? This is like the next one. So the previous one, so I can use x of n minus 1. So now I'm trying to copy this side now. The previous one minus f of x n minus 1 all over the derivative. Now if this is not good, because you're like, I don't like this n minus 1 notation, that's fine. We can do it the other way around. We can say that the next value, x of n plus 1, is equal to the current value, x sub n, minus the y value evaluated at the current value of x, which is x sub n, divided by f prime of x sub n, the slope at the current value of x sub n. So really what I'm saying is this is like current, and this is the next value. So as long as you understand that the x of n plus 1 is the next value, I think you'll be okay. All right, most textbooks use, I think, this notation here, but I have seen some use this as well. So just be aware they both mean the same thing. So let me try to illustrate this now by doing 2 questions for you, and then that'll be it for this video. So do 2 iterations of Newton's method with the given initial approximation to find the root of this equation. Okay? So really, once again, I'm asking you to find x using the formula that I put in the box in green. But before we do that, remember, our function always has to be something equal to 0. So I'm going to move everything x cubed plus x squared plus 2, make it equal to 0, because we need that. Okay, and so therefore my function f of x is x cubed plus x squared plus 2. We also need to calculate the derivative. That's 3x squared plus 2x. And then now we're ready to plug it into the formula. So our next value, I'll say x sub 1, equals our initial value of x sub 0 minus f of x sub 0 all all over f prime of x sub 0. The question is, what's x sub 0? Oh, we know. It's actually the value of negative 2. So in this case, let's plug in negative 2. Negative 2 minus, and then we have to evaluate. Negative 2, we'll plug it in. Negative 2 cubed plus negative 2 squared plus 2. There's my top, my numerator, which is just f of x. And then we'll divide this by the derivative, 3 times negative 2 squared plus 2 times negative 2. Okay? You can do these calculations yourself, blah, 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 and then ding, the answer is negative 7 over 4. So notice, look, we started with x sub 0 at negative 2, and now our new guess for our x-intercept, our new value at x sub 1, is equal to negative 7 over 4. So now if I want to find the next approximation, which is x sub 2, I would ask you to now once again plug it into the formula and calculate it again. This time our current value will be x sub 1. So x sub 1 minus f of x sub 1 all over f prime of x sub 1. We're going to now plug in the value of negative 7 over 4 into x sub 1. Oopsies. And then, unfortunately, we're going to have to do the same thing to these ugly polynomials. I kind of want to do this. Aren't you glad I'm doing it on video for you? Because, bam, the answer is, yes, I'll tell you, negative 1.6978. And so there is your 2 iterations. So you took your initial guess of negative 2, and then you plugged it in. And now after 2 iterations, my new approximation for the root is negative 1.6978. Okay? And you're thinking, well, how many times do I do this? Well, it really depends on how many decimal places you want accuracy for. So in example number 7, I'm saying now let's use Newton's method to find out what the 5th root of 2 is. And I want it correct to 6 decimal places. How many times are you going to have to do this? Well, you're about to find out. So let me at least start you off. I said this is the solution. So really the question is, what was my function? What is the question? What am I actually trying to find here? If I already told you the cube root of 2 is my answer, x, perhaps we want to figure out what our function will be. So if I can cube, the 5th, take the power of 5 on both sides, I get x to the power of 5 equals to 2. If I were to move everything to one side, because remember the idea is to get something equal to 0, now you see that I have a nice polynomial. F of x must be then x to the power of 5 minus 2. Because ultimately I want this x to the power of 5 minus 2 to be equal to 0. I want to find out the x-intercept. So knowing that, of course, we can calculate the derivative, f prime of x. That's just 5x to the power of 4. All right. Now we're set. Let's plug it into the formula. Here we go. Here's our Newton's method formula. X sub 1 equals x sub 0 minus f of x sub 0 all over f prime of x sub 0. Just remember that the prime is always on the denominator. The y value is always on the top, the numerator. Oh, we forgot one thing, didn't we? What's our initial guess? So, of course, if you can make a great initial guess, then you don't have to do it as many times, but I'm not too sure. I'm predicting, I don't know, what would be a good x value to guess? Let's try 1. 1 to the power of 5 is 1. 1 minus 2 is negative 1. That's okay, but yeah, let's just do that. And so let me just say my initial guess, and I'll do that over here. Initial guess. And the notation for the initial guess is x sub 0. I'm just going to choose 1. Okay? You can choose like a decimal, doesn't matter, but I'm just going to choose 1. So here we go. So x sub 0 is 1 minus 1 to the power of 5 minus 2 in the numerator, 5 times 1 to the power of 4 in the denominator. That's 1 take away, what's that? 1 minus 2 is negative 1 over 5, so that's 1.5. Oops, that's not 1.5. That's 1 plus 0.2. That's actually 1.2. Okay, so that's my new approximation. Is that correct to 6 decimal places? No, I only have 1 decimal place right now. So guess what? Let's do it again. x sub 2 equals to x sub 1 minus f of x sub 1 all over f prime of x sub 1. So now we're going to use the value of 1.2 and do the same thing. So 1.2 to the power of 5 minus 2 all over 5 times 1.2 to the power of 4. Calculator time, and I get this, 1.152901235. Notice now I'm getting better with my answer, but I still don't have any decimal places repeating from the previous answer, so I'm not too sure if this is good enough either. So guess what? Let's do x sub 3. Blah, 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 right? Blah, 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 blah. Blah, 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 blah. And in this case, you get the answer 1.148728887. So getting closer and closer, okay? Now, I want you to go ahead and try the rest, but I'll tell you that if I want 6 decimal place accuracy, I'm going to get my final answer. I won't tell you how many iterations you need to do this for, but don't worry, I'm not going to make you do this 10 times. But my best guess will be 1.14869. 1, 2, 3, 4, 5, 6. Okay? All right, so you work on that, and then once you're done that, you can go ahead and try some of the questions that I've done here with differentials and also Newton's method. All right, go to it.